Well, this little presentation is entitled Transforming Your Understanding of Transformations. Now, wouldn't that be marvellous? So I'm going to endeavour to do that. So this is quite a long one actually. I'm going through the whole kit and caboodle of transformations, including matrix transformations. So make sure you fasten your seatbelts and we'll have a go at it, okay? I hope this will clear a few things up if you have any problems. Now, this is me. And you can see I'm looking happy. But once upon a time, I was very sad because I couldn't understand these transformations. And I used to ride my bike backwards and forwards to school, thinking about them, thinking about them, thinking about them, trying to work them out. And then one day, I discovered a treasure. And that was the treasure I needed. And in particular, I found the key to open that treasure. And that treasure led me over a beautiful rainbow to the promised land of transformation understanding. You see, once upon a time I was very sad, and I used to always sigh because I couldn't understand these things. They were like double Dutch. But searching and searching and searching, and necessity being as it was, led to the inventions that I've found and a complete understanding I hope I have now, which I'm hoping to explain to you. So what did I do? I found the treasure, and that made me happy. So I jumped in and I found the key, and then I ascended over the rainbow above the valley of sorrows and pain into the promised land. And yes, I was happy. So I'm hoping to make you happy today, the same way as I was. Okay, now, here's the treasure chest, and when you have the key like I found it, I opened it. And what was inside? Let's think about that. What was inside? Well, here comes the genie out of the musty old treasure chest, and what's in it? There is the key to understanding all these things. X prime equals ax plus b, and y prime is equal to cy plus d. That is what all this kerfuffle is about, and it is just so jolly simple. If you can just get that little concept, you'll be happy. Let's take an example. We have an original function, and that consists of points x comma y. And then we have our transformation cloud coming out of that chest, of treasure chest, and when we have the transformed function, which we're going to call, I'll call them x dash and y dash, okay, because I'm more used to that symbol rather than x, that terminology rather than x prime, y prime. Now, we're going to call the original function the caterpillar, which gets transformed into the butterfly, okay? That's going to be our logos for this presentation. Now, there's what you do to transform the left-hand side original function to the right-hand side transformed function. That little formula, x dashed equals ax plus b, a linear transformation relationship. Sometimes there's a little bit of y thrown in as well, but we won't complicate things with that at the moment. It's not all that complicated anyway. Sometimes they do that when we're looking at inverse functions, things like that, where you swap x and y. Okay, and there's the other side of the coin, which is y dashed equals to cy plus d, and as I said before, sometimes you might add a little bit of x in there as well, if you have inverse functions, that kind of thing. So that's really all it's about. It's very, very simple. So we have our transforming cocoon, if you like, for our caterpillar to get into the butterfly, and all the problems that you will get, they either start at the original function, the caterpillar, and they ask you to come up with the transformed function, and I call that going forwards, and they will give you a set of transformations to enable you to work that out, or alternatively, they will finish there, that's right, or alternatively, they will start with the finished transformed function, and they will get you to go backwards to find from an original function what the transformations were. That's what they will generally do. And in the case of matrix transformations, they'll just ask you to find the code. The code, not just a description of the transformations, the actual code itself, but written in matrix form. Okay, that's what it's all about, folks. Now, that transforming cocoon is the absolute essence of the whole thing. The whole thing. So, this is what I call the key to that treasure chest of transformation bliss in the promised land, okay? So, let's see whether we can just unlock this whole story with that key. Right, now what are we doing now? We're going forwards from an original function to the transformed function, and then we'll do some examples of going back the other way and see what it looks like. Right, so we're going from x comma y, which is the original function, and we're going from there to x dashed y dashed. That's what you're supposed to be working out with these things, okay, the transformed function. Okay, now there are two different ways of doing this. Two different ways of doing it. First of all, there's the traditional or formal way, which has a logical basis to it, using the key. We use the key. We find the key, and then we apply that key to get the transformed function. Or there's what's called the shortcut or learned technique, which is more of a rote memory technique, which in my way of thinking has far less logic to it, because it doesn't seem to make sense unless you go into it very deeply, and then even then you have to remember what the various recipe steps are for various transformations. We'll do an example of the first one, I think. The first technique, method 1, or technique 1. Okay, ooh, look at that. So what have we got here? We've got a graph y equals x squared, and we're going to sketch the graph of the image under the following sequence of transformations. A translation of 1 unit in the positive direction of the x-axis and 2 units in the positive y-axis direction. Thirdly, a dilation of a factor of 2 from the y-axis and a reflection in the x-axis. And we have to state the rule of the image. Well, it sounds like a lot of demands on us, but hey, remember, inch by inch, anything's a cinch. And all we've got to do is find the key and apply that key, okay, to find our function. There's step 1, there's step 2, or transformation 1, transformation 2, transformation 3, transformation 4. Okay, so, and in order to do this, it's a very visual procedure, so I'd like you to get used to drawing a picture so we can actually chart what happens to x comma y as it goes along its journey to become x dashed y dashed. Okay, let's see what we got here. There's a nice little picture for us. And there's our original point x comma y, and we're going to apply transformation 1 firstly to it. So, what are we doing? We are translating at 1 unit in the positive direction of the x-axis. That means we're adding 1 to the x. So that's our new point, x plus 1 comma y. Okay, what happens when we apply the second transformation? It goes up 2 units in the positive y direction, so it's now x plus 1 and y plus 2. Okay, number 3 coming up. What do we do to it? Dilate it by a factor of 2 from the y-axis. Now, away from the y-axis means it's moving in the positive x direction. Okay, so you've got to multiply the x coordinate by 2, and you get that result there. Now, that's very simple if you think of it visually. Don't get yourself messed up. Please draw a picture, and you'll be okay. The fourth step, we're reflecting in the x-axis, so we're going, the x-axis is acting like a mirror, which means that the y-coordinate goes to its negative value, so it becomes minus y plus 2 in brackets. Now, all of that gets us to our new point, which is x dashed and y dashed. That's the transformed coordinates, okay? Now, that's going to give us our key. So, this is the nub of this technique, okay? So x dashed is 2 times x plus 1 because they are equivalent. And y dashed is minus, open bracket, y plus 2, close bracket. That is the key, and that's the key to everything, okay? Now let's just take a step back and think. What is the original function here? Yes, it's y equals x squared, and we are going to work out what our new function is using the key, okay? Now it just so happens, we don't know what we're ending up with yet, just so happens that that y value in the key is equivalent to that y value in the original function. It is equivalent because they are the same thing. Both of them are untransformed values of y. The same thing applies to the x value in the key and the x value in the original function. So what you have to do, and what I have to do, is substitute those x and y values from the key into the original equation. But as you can see, they're not in the right form for us to substitute them in just now. It would be better for us if we could make them the subjects, and then we would be able to see what we're doing, the subject of those equations. So let's do that now. X is x primed over 2 minus 1 after a bit of manipulation, and we get y is minus y prime minus 2, or dash I mean, not prime. Okay, now all you do now is just plug away into that y equals x squared equation. And we're going to do that over the page, I think. Yes, I'll just rewrite those last few lines before, just so that we'll know where we're up to. Now that's where we got to, okay? Now let's actually do it. Okay, that looks pretty good. Now that's the equivalent of y equals x squared, written when we've made x and y the subject of those key equations, okay? And then all we've got to do now is fiddle around with the algebra to work out what y dashed or y prime is, okay? And that's what I'm doing there, making it look a bit more friendly. And yes, I've just added 2 to both sides. I'm nearly there now. I've got to multiply by minus 1 to both sides, and I think that's it. That is my y prime in terms of x prime, or y dash in terms of x dash. And what I'm going to do now is I am just going to drop the dashed or the prime notation because I've reached my end result. That is my transformed function, okay? That's the butterfly function. And there it is. There it is, okay? So isn't it easy? The key, as I said, is the key to doing it. That's the key. Okay, now we're going to sketch the graph, as they asked. Let's see. That's a simple matter. You've done all that stuff 1,000 times. We've just got to work out what the intercepts are, and it's an upside down graph, upside down parabola graph, and probably work out where the turning point is. If there's no x-intercept, which I don't think there is, because it looks to me like the turning point of that thing is x is plus 2 and y is minus 2, and it goes downwards from there, so there's going to be no x-intercept. So we will work out the turning point. So when x is 0, y is minus 3, I worked that out, and I've just given you the answer there. And when y is 0, there's no solution for x, as I was saying. Okay, the turning point would, as I said, is x is 2 and y is minus 2. Now I think we're ready to sketch a Rooney now. Woohoo, here it comes. Now, I'm putting a scale on there. In the exam, please put a scale on your graphs if there isn't one there. They will probably take marks off you if you don't. So there is my y-intercept, as I just worked out below. And you notice I've given it as an intercept point. Please do that, unless they ask otherwise. There's my x scale, and now I'm drawing the graph. And alakazam, here comes the turning point, and I think that's it. Oh, hey, there's my butterfly function. Isn't that beautiful? I'm just going to label it. There it goes. And that came from y equals x squared, which is my caterpillar function. Get the idea? I hope the pictures help, you know. I think pictorial presentations are pretty helpful when you're doing such abstract stuff as what this is. Okay, that was method 1, what I call the logical approach, but it's a little bit longer than the shortcut learned approach, which to my mind does not have a lot of logic to it at first glance, unless you really probe deeply into it. So I've just rewritten the question, and now we're going to do example of method 2. Okay, right. So this is a learned shortcut technique. Yeah. So what you do is here comes the transformations, 1, 2, 3, 4, and we start with y equals x squared, and this is a cookbook recipe technique where you, depending on what you do, you replace y or replace x with something else, and you have to learn them, okay? And they're different. It's a different technique altogether from what we've just done with the rigorous key technique. So transformation 1 requires us to replace x with x minus 1. If you move x in the positive direction, you have to replace x with x minus 1. So we get that. Okay. Now technique transformation 2, we've got to go up 2, so that means you've got to replace y with y minus 2. Now you are going to have to learn these if you don't already know them and you want to use this technique. It is a good technique to use if you want to be fast, okay? And in an exam, yes, you do have to be pretty fast. So, but you have to be confident. If you're not confident with it, use the first technique. And it's good to use the first technique because the key thing is what this stuff is all about. Now, yes, you replace y with y minus 2. Now, transformation 3 is the dilation of a factor of 2 from the y-axis, so you have to replace x with x over 2. It's kind of like a game of opposites, this stuff. So, and that gets us that funny thing. You notice that you don't replace all of x minus 1 with x minus 1 all over 2. No, you don't do that with this technique. It's only the x term. And transformation 4, it's a reflection in the x-axis. That requires us to replace the other one, y, with negative y. And that's what we get. And there it is. Now, if you clean that up a bit, it'll be exactly the same result as what we got with the key technique just previously. And there it is. Wacko! There it is. That's the final result, which is exactly the same. Oh, there, what's that? The butterfly function. How lovely. And that was what we got as before with the previous technique. Okay, now that's 2 examples of going forwards. Okay? Now we're going to go backwards. You notice in this slide, the butterfly is going backwards to the caterpillar. So we've got in these instances, they'll give us a finished transformed function, and they will give us a starting function, the caterpillar function, and they will ask us what were the transformational steps we applied, or in the case of matrix ones, they'll say what was the transformation matrix, which is just another fancy way of looking at the steps involved. It's the code, okay? It's the actual key written in matrix form. Alright, what do we got here? So what have we done? We've got a sequence of transformations that maps the graph of y equals 1 over x. That's the caterpillar function onto the graph of y equals 4 over x plus 5 minus 3. That's the butterfly function. And use this to sketch the graph of y equals 4 over x minus 5 minus 3. Stating the equations of the asymptotes. And well, we're not going to do all that bit. We're just going to do the transformation steps. Can we? Please? Yes, thank you for giving me permission to do that, because it's going to be long enough anyway. This video is going to be a long one. Okay, let's go with, what are we going to, yes. Now I'm just writing it, so I'm just stating it in words of one syllable. Going backwards, okay? There are 2 methods. This one is using the key, okay? The second one is using a learned technique again called Dr. T. Good old Dr. T. He's like Doctor Who. And because he's stranger. He's very strange, but he works pretty well. Alright, so just to reiterate, that one was the starting function, that one was the finishing function. So I've put little red dashes on the y and the x of that butterfly function, you'll notice, okay, just to emphasize the fact of what I'm doing here, because this uses the key, the rigorous technique, and I've labeled them equations 1 and equation 2. Okay, here comes the working. That's equation 1, that's my starting function. This one's going to be equation 2, that's my finishing function. Okay, and look, note the dashes on the y and the x in the finished function. Now I'm going to get my key which unlocks everything. Okay, that's right, find the key, and for you and me. Now, this is we're going to manipulate this function so it looks in a transformed form where we haven't been fiddling with it to make it look cosmetically better. In other words, that minus 3 is an orphan term, and really it belongs to the y. So we're going to put it back with the y, okay? And that 4 really doesn't belong to the x. It's better to basically make it over the y term so that we've left a 1 over x plus 5 term which looks more similar to the function above, the untransformed one, okay? So let's do that. There's y prime plus 3 over 4, that's right, equals 1 over x prime plus 5. Okay, now that function, that equation, I mean, looks very similar to the equation 1, which is what we want, because y plus y dashed or y prime plus 3 over 4 equals y. They are equivalent. They are equivalent because if you plotted the function y prime plus 3 over 4 against 1 over x prime plus 5 on the x-axis, you get exactly the same curve as if you plotted y equals 1 over x. That's why they are equivalent. Don't ask me why that is. I haven't got time to go into it now, but it is true blue. Okay. Right. X prime plus 5 equals x. You can just read it off. They're equivalent too. And now we're just going to solve that for our key, which is the key to everything. So that's y dashed plus 3 equals 4y, which gets us y dashed equals 4y plus 3. That is our key. Yippee for the key, because we can just read the transformations straight off, okay? Also, we know that x prime equals x minus 3, and that's the key. Oh, x minus 5, I mean. That is the key for you and me, and now I can just read them off with glee. Yippee, the key. So y prime or y dash equals 4y plus 3, which means we've got a y stretch, a dilation of a factor of 4 from the x-axis, but it's a y stretch. Make no mistake. Now, and we've also got a translation upwards in the y direction by positive 3 units. See how easy it is if you just use the key? It's just so easy. Okay, I've just written that out in purple for you. Dilation of a factor of 4 from the x-axis, as I said, and a translation of 3 units up. Just fitted that in, didn't I? So that's it, folks. I've just read them off for you, and it's easy as if you use the key. Now, I think we're... yeah, okay, that's the x prime minus 5 there. That's 5 units. Oh, that's right, I forgot that. The x prime equals x minus 5 means we're moving 5 units to the left, okay? Now that to me makes perfectly logical sense. And I've written it out in purple again for you, what it is. Now, we're going to do the Dr. T technique now. This is the one that virtually everybody uses. But again, it's a non-intuitive approach. You just have to learn what it all means, okay? So, Dr. T. Hello, Dr. T. And we're going into outer space with Dr. T. A shortcut learned technique, yes. But it's fast. That's why people use it. Right, so here's what we've got to do. We've got to, the same question, and we've got to identify the transformations. And we're not going to do the plotting with all the asymptotes and all the rest of it, okay? I'm just going to show you how to do it. I put some dashes on the y and the x term because I've identified which function is which. The y equals 1 over x is the original caterpillar function, and that y dash equals 4 over x dash plus 5 minus 3 is the butterfly function. That's why I put the dashes there. And you can do that just as easily as I did. You can identify which one is which, because that's the secret to the whole thing. Okay, so with this technique, you rewrite the transformed function in that form, again, like we did last time, and then you just read them off in accordance with a specific order, which you have to learn. It's D, then R, then T. You must do it in that order, otherwise it's going to be wrong, particularly with you can't mix the R and the T up, because you'll get into all sorts of trouble if you do. So just remember Dr. T for you and me. D is for the dilations, which is that one I just put a red circle around. That is and you just have to learn what that means. That's a dilation of a factor of 4. It's a y dilation, therefore it's from the x-axis, away from the x-axis. Now in this case we haven't got any reflections. If we did, there'd be a minus sign outside either the y term or the x term. But we do have two translations, and it's like a game of opposites again. When you see a plus 3 next to the y, that means it's gone down 3. And if you see a plus 5 next to the x, it means it's gone negative. In other words, 5 to the left with the x. So that's Dr. T. Always, as I said in purple here, specify the transformations in the D to R to T order. Otherwise, you'll be in more trouble than Doctor Who. There you go. Alright, now we're going to do forwards with matrices. Good grief, matrices. The bane of students' lives. However, they don't need to be the bane of students' lives. They're just as easy as 1, 2, 3 when you have this key thing happening, okay? Now these are official Victorian Curriculum and Assessment Authority questions from past examinations. So this one's a forwards one. It's a multiple choice question, and it's asking us, it's saying to us a transformation T such that x and y values, that's all that means. Two-dimensional plane, r squared means a two-dimensional plane of x, y values maps to a two-dimensional plane of x dashed, y dashed values with the rule. And you see that T and the matrix XY in the matrix, that just means X dashed Y dashed. So please get that right, okay? And in other words, they're giving us the key. They're giving us the key. That's what that matrix is. And they're asking us to come up with the finished transformed butterfly function. So we just got to unravel that key a bit. Yeah, it is. That's the key for you and me. Now, which function's which? That's really important to identify. Don't get ourselves mucked up. That y equals x cubed is the original caterpillar untransformed function, and options, either one of those options, A, B, C, D, or E, is the transformed butterfly function. We are going to use the key to find out which one it is, and it's easy to do. Easy. So, we've got x dashed, or x prime, equals 4x plus 1. Now, I just read that straight off that matrix, okay? 4 times x plus no times y plus 1, okay? You can do that too. And y dashed, or y prime, equals no times x minus 2 times y plus 3. Did you do that with me while I was doing it? Good. Now, once I got this key, my goodness, it opens the treasure chest, and we're going to go over the rainbow again. That's the starting one, that's the caterpillar one, and we just simply have to, that's right, we just have to basically recognise that those x's are equivalent from that key, and those y's from the key are equivalent. So we first have to rearrange the key equations so that x and y are the subject, so we can easily plug them in to that formula and get our transformed butterfly function. That's right, they're equivalent, all right. So here we go. Substitute for x and y. We have to substitute for x and y into the key, but let's make them the subject first. And there's y as the subject, and there's x as the subject, and substitute. What are we going to get? Probably a bit of algebra to fiddle around for a while, but it's going to be easy. Another step, I think so I've basically cubed that 1/4 term in the right hand side bracket, multiplied by 2, actually minus 2 as well from the left hand side, and that's what I got. Now all I've got to do now is add 3 to both sides, I think. Yeah, now you pray and you look for it in the options, and you make jolly sure that they have it, that you don't pick the wrong one, because it's really confusing. They're all very similar. Now, is that there? Can you see it? Are you praying? Oh, I think I've just seen it. I think it's A. Oh, relief. You see how beautiful the key is? Isn't it wonderful? So we've done it, you see, and look how easy it was. So don't be confused. If you are confused, just go over this video again. Now we're going to do the last one, which was backwards with matrices, okay? Backwards with matrices. And this, again, is an official VCAR question. So this time, they're giving us the starting function y equals x, sine x, onto the curve with equation y equals something considerably more awful with sine x in it. And so that's the butterfly one. The first one is the caterpillar one, the y equals sine x, and they are asking us for the transformation steps, but in the form of the code, okay? So we can easily work that out. We've just got to find that code and then put it into matrix form, and we're laughing, okay? So that's the caterpillar one. That's the butterfly one. So we're going to put primes around those x and y terms, or dashes, whichever way you look at it. Okay, and we have to find the code. And once we've found the code, we'll put it in matrix form and everything will be beautiful. And we're over the rainbow again, into the promised land. Right, so that's what we've got. Y equals sine x goes to that monstrosity over there with dashes on the x and y terms. Yes, they are equivalent. Yes, they are, because we've rearranged the transformed equation to bring the orphan terms back to the y and to divide by -3, both sides, so that you've just got a normal sine term on its own to be equivalent to the sine term on its own in the caterpillar function. So it's just a matter of, yeah, that's right, the x terms are equivalent as well. So it's just a matter of now equating them now. That's the y terms are equivalent from butterfly to caterpillar, and the x terms are equivalent from butterfly to caterpillar. Now all you do now, folks, is you just make x prime and y prime the subject, because that's what that matrix is, and then put them into matrix form and then pray again. Hopefully it'll be there. Okay, making great progress. X prime is equal to that thing. Now let's put that in matrix form. Goodness, look at that. Now, you've got to look and see whether that's equivalent to what I had above. Okay, so I'm saying x prime equals a half x plus no y minus pi on 2. That's right. And on the lower line, so y dashed, or y prime, equals no x minus 3y plus 1. Look, by George, I think that's right. Now, are you praying hard? Because we're going to see if we can find it. Is it there? They all look so similar. Be very careful. Oh, do you know, I think I've found it. I think it is D. Is it? That's right, the key in matrix form. Yes, yes, yes. My goodness, aren't we happy now? We've done it. That's it. So, don't be confused, just have a go, and you'll get to the end of the rainbow, into the promised land, and you'll be a happy, happy chappy. Okay? My goodness, that was long, wasn't it? Thank you so much for listening, and I hope you get it. If you don't, just have a look at it again, okay? Alright, see you.